This is the introduction to light video for our Honors Matter and Change class. So we just finished learning about the basic history of how the atom was discovered and its subatomic particles were discovered along the way. And we ended last unit with the model of the atom looking like a tiny, positively charged nucleus with the electrons flying around somewhere outside of the nucleus. That was after the discoveries of Rutherford and Chadwick. Now, the atom is mostly empty space and there's no organization to the electrons, according to the model that we just left off. But it leaves us with a few unanswered questions. And one of those questions is, if the nucleus is positively charged and the electrons are negatively charged, then why don't the electrons get pulled into the nucleus, since opposite charges attract? So there's some unanswered questions, and so our model of the atom is not quite complete. And this leads us to the next set of researchers that were working right around the same time as each other at the beginning of the 20th century. And interestingly, most of them were studying light in some way. Now we need to take a few minutes and talk about light. And as you guys should already know from middle school, that light is a type of energy that at the time most researchers believed acted like a wave. And you know that waves have certain characteristics that we can study and discuss. And two of those characteristics that are important for this lecture are wavelength and frequency. Wavelength is the distance between two identical places on a wave. As you can see in this diagram, you can look at the wavelength if you measure from two identical places. You could also measure from the trough to the next trough, but that's the wavelength. And then the frequency is how many waves pass by a certain place during a given period of time. So the unit that we use for wavelength is meters, although sometimes you might see them expressed as nanometers, or if we're talking about really big waves like radio waves, they might even be in kilometers. In frequencies, unit is hertz, and it's important to understand that the hertz is 1/second, or it's the inverse second. So please keep this in mind as we start to do calculations in just a few minutes. So that's important to understand. Now light, the light that we think of is usually visible light, and it's only part of a larger range of energies that we call the electromagnetic spectrum. Now if we take a look at the electromagnetic spectrum, you'll notice that as wavelengths get shorter, the frequency of the waves get greater. Or in other words, you can think of how often are the waves vibrating in space. So as we move from right to left, these wavelengths are getting shorter and the waves are vibrating more and more frequently down to this very end where we can't even see the wavelengths there. Now that's an important relationship that we'll discuss in a few minutes, this relationship between wavelength and frequency. But frequency is directly proportional to energy. So the higher the frequency, the more energy the wave has. And you can think of the amount of energy as it relates to the harm it could cause tissues. Radio waves, on this end of the electromagnetic spectrum, have really low frequency. They have big wavelengths but low frequency. So that means they have low energy, and so they're not very harmful to tissues. Ultraviolet rays, X-rays, gamma rays, they have much, much higher frequencies. So that means those forms of energy are much, much higher, and they can cause tissue damage. As you know, X-rays are damaging to certain developing tissues. Gamma rays can penetrate tissues and cause cancer. Or if you're a Marvel comic fan, gamma rays are what caused or created the Incredible Hulk, but we can talk about that later. Now if we look at another version of the electromagnetic spectrum, now this is backwards from the previous one. So radio is on the left-hand side and gamma rays are on the left-hand side. And here we have the visible light spectrum, but it's been broken down, so it's been taken down. And so you see Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. And if you want to, remind me, there's a fun music video that we can watch about Roy G. Biv. But it's important that you have a general understanding of how energetic these types of radiation are. So one way that you can remember that is by this sentence at the top, that really tall men in Venice usually excite Georgina. And so the underlined letters refer to the types of radiation. So radio, television, microwave, infrared, visible, ultraviolet, X-rays, gamma rays. If you want to come up with your own sentence, you can. This was actually created by a student several years ago, and it just kind of stuck, and I like it, and that's how I remember the order of energies for the electromagnetic spectrum. It's also important to look at the visible light. That red is on the lower end of the energy, where violet is on the upper end of the energy. And the way that I always remember that is I do remember that ultraviolet rays can be harmful. So violet is right next to ultraviolet. So this must be the higher frequency of the visible spectrum. So if it's higher frequency, it's shorter wavelength. The red, longer wavelength, lower frequency. Okay. Regardless of what type of radiation we're talking about, whether it's visible light or X-rays or gamma rays, all forms of electromagnetic radiation travel at the same speed through space or through a vacuum. And that speed is 3.00 times 10 to the 8th meters per second. That's a value you need to know, so you might want to jot it down because you'll need it when it comes time to doing some calculations in just a second. And we also talked about how wavelength and frequency of the radiation are inversely proportional. So as the wavelength gets bigger, as we go up, the frequency gets smaller. Wavelength and frequency are related. They're inversely proportional, but when we multiply them together, we get the speed of light. So that's how all three of these characteristics of radiation or light are related to each other. So you might want to get this formula down, that the speed of light is equal to the wavelength times the frequency. And we're going to do a sample problem. So if you need to pause right now because I might be going too fast, you might want to do that. But I'm going to continue on with this problem. So a sample problem might be asking you to find the frequency of light if you know the wavelength. So we have the formula at top. So the speed of light is equal to the wavelength, and that's the lowercase lambda in the Greek alphabet if you're curious, times the frequency. And we want to rearrange this equation to solve for frequency. So the frequency of a light or any type of radiation is equal to the speed of light divided by the wavelength. And then we just plug in our values. So we don't know the frequency. We do know the speed of light, 3.0 times 10 to the 8th meters per second. And I am going to put the units in here so you understand where the final unit comes from. And we have our wavelength, 4.257 times 10 to the negative 9th. So we're talking in the nanometer range here. So I plug my values in. You guys know how to do that, but look what happens to the units. Meters cancels out, and I'm left with 1 over second there, or inverse second, or hertz. So that's how the units are related to each other. So if you plug these values into your calculator, and hopefully you're doing this problem along with me so that you know how to do it in class next time. You plug those two values in, you should get something 7.05 times 10 to the 16th hertz. If you did not get that answer, double check your math. Again, sometimes when you're plugging in scientific notation into your calculator, it's a little particular. There's the bell. You're not dismissed. So double check how you've typed it into your calculator. If all else fails, put your values from your denominator in parentheses and your values in the numerator in parentheses and see if that alleviates any exponent issues that you might be having. So be sure that you understand. So that's just general relationship of light and wave properties. We can actually use this for any type of electromagnetic radiation that we've discussed today. But let's get back to the discoveries. So far we've been talking about light acting as waves, but some experiments that happened were getting results that couldn't be explained by light acting as a wave. So we have some issues. So you think you know how something is acting, and then you get an experiment that's giving you different results. And the most notable of these, sorry about that,